Well, for the last talk today, it's my pleasure to introduce Nicoletta Tardini from University of Parma, and she will speak about Dolbeault and Bott-Chern harmonic forms on almost Hermitian manifolds.
Thank you. And of course, let me thank the organizers for the kind invitation to be here and give a talk. So yeah, it's my first time in Brazil, so I'm really happy to be here. Okay, so I would like to present some results obtained in joint papers with Andrea Cattaneo and Adriano Tomassini from the University of Parma and Riccardo Piovani from the University of Torino. So the results are about harmonic forms. So harmonic forms in the sense of Dolbeault and Bott-Chern on almost Hermitian manifolds. So the setting for this talk will be almost Hermitian geometry. Okay, so, well, the plan of the talk is the following. So first of all, I will start with an introduction in order to fix some notations. Also, in order to motivate at least why I was interested in studying harmonic forms in this non-integrable setting. And then I will move to consider four-dimensional manifolds. So in the second part of the talk, I will consider almost Hermitian four-dimensional manifolds. And then we'll see that we can say several things about the Dolbeault and Bott-Chern harmonic forms in this case. And then in the final part of the talk, I will consider higher dimensional manifolds. But in that case, I will need to put some stronger assumption on the metric I'm considering. And I will consider, in that case, almost scalar metrics. OK, so the setting is the following. So just for notation, so during the whole talk, I will denote with X compact, smooth manifold of real dimension 2n. And J will always denote an almost complex structure on the manifolds. OK, so in general, I'm not assuming J to be integrable. OK, but anyway, so we have J. So we all know that the complexified tangent bundle splits into eigenbundles with respect to the eigenvalues I and minus I. And so since also J acts on the space of forms, we have a natural B degree on complex value differential forms. I mean, we know that the space of complex value differential forms can be decomposed as the sum of PQ forms on the spaces of PQ forms. And well, the thing is that according to this decomposition, also the exterior derivative splits on almost complex manifolds. But if J is non-integrable, we do not just have, the 1, 0, and 0, 1 components. We do not have just del and del bar in the decomposition. But we also have two extra terms, two extra differential operators that I will call in this talk mu and mu bar, that are of B degree +2 minus 1 and minus 1 plus 2. OK? All right, but, well, of course, I mean, if J is integrable, one of the possible characterization for the integrability of J is saying that mu and mu bar vanish. So in fact, the exterior derivative is just the sum of the operators del and del bar. So let me just recall a few things on complex manifolds that, I mean, of course, we all know. So using the fact that this squares to 0, we find, the usual very nice relation for the operators del and del bar. I mean, they both are differential operators. They square to 0, and they anti-commute. OK, so what we have on a complex manifold is the space of PQ forms and these two operators del and del bar satisfying these relations. So we have a double complex. And every time we have a double complex, we can define several cohomology groups. For instance, on complex manifolds, we can consider the Dolbeault cohomology, right? So we use the fact that del bar squares to 0, so we quotient del bar closed forms by del bar exact forms, and we define this cohomology. We can do the same, of course, for the conjugate operator. And we also can define on complex manifolds the so-called Bott-Chern cohomology groups and Deightley cohomology groups. Okay? They are defined using both the operators del and del bar. And these quotients are well defined because we have these three relations. Okay? And well, so on complex manifolds, we can define all these cohomology groups. They are, if the manifold is compact, They are finite dimensional because we have Hodge theory for these cohomology groups. So they are finite dimensional complex vector spaces. I mean, they're very useful holomorphic invariants to study complex manifolds when the almost complex structure is integrable. Okay? And, well, just let me recall that, so in general, these cohomology groups on a complex manifolds are related by this diagram. I mean, we have that the maps in this diagram are the maps induced by the identity. So for instance, the identity induces a natural map between the Bott-Chern cohomology and the Dolbeault cohomology. And this map, well, it's the one induced by the identity because if you have, so let me go back to the definition of Bott-Chern cohomology. So here, the classes here have representatives that are forms that are both Dobar closed and declosed. So in particular, since they are Dobar closed, essentially you have this map. Okay, and so on with all the other cases. Okay, so on every complex manifold, you have a diagram like this, but be careful because the maps in this diagram are in general neither injective nor surjective. Okay, they are not isomorphisms in general. In fact, they are isomorphisms if and only if the manifold satisfies the Dobar lemma. This is famous results by Deligne, Griffiths, Morgan, and Sullivan in the general setting of double complexes. So in particular, when your if you have a compact Kähler manifold, it satisfies the Dobar lemma, so these cohomology groups are isomorphic. Okay? So what I just want to say is that these cohomology groups are very useful if you want to study non-Kähler manifolds, because in that case, they really are giving you different pieces of information. Okay? All right, so what happens when J is non-integrable? Because we have these two extra components in the exterior derivative, so we can, do this easy calculation using the fact that this squares to 0, but now we have, more relations, of course, for all the operators that are involved in this splitting. So in particular, for instance, let's see, we have 7 relations, or if you want, 4 relations and their conjugate. So what we have is that, well, either both mu and mu bar squares to 0, and notice that the bar square is not 0. Of course, it's 0 if and only if the J is integrable. And in fact, what you have these extra terms appearing here, and also del and del bar do not anticommute anymore. Again, they anticommute if and only if J is integrable. Okay. So this is just to say that when you have an almost complex manifold, you cannot define the Dolbeault cohomology groups. You cannot define the Bott-Chern cohomology groups. I mean, actually, you can define the standard Dolbeault cohomology if and only if the bar squares to 0. So it means that your manifold is a complex manifold. Okay. Okay. So, however, if you fix a Hermitian metric on your almost complex manifold, you can define the Dolbeault Laplacian in the usual way. You can take the bar star operator, you can consider the commutator of the bar and the bar star, and you get an elliptic operator. So if X is compact, and you take the kernel of this elliptic operator, you have a space that is finite dimensional, even though J is non-integrable. Okay? So for this talk, I will denote with this small h, so the dimension of the spaces of Dolbeault harmonic forms, and I will call these numbers Hodge numbers. Okay? For this talk, the Hodge numbers will be the dimension of the spaces of harmonic forms. And well, of course, you have the usual characterization for harmonic forms. So a form is Dolbeault harmonic if and only if it's closed and co-closed for the operator Dobar. Okay, so well, if J is integrable, clearly we are on a compact complex manifold. I'm assuming X to be compact. So we are on a compact complex manifold. So in every Dolbeault cohomology class, there exists a unique harmonic representative. Okay, we have Hodge theory. So we have this nice isomorphism that it's very useful. I mean, in many cases, when you want to compute the Dolbeault cohomology, you compute the harmonic forms. For instance, on nil manifolds and Soule manifolds is a standard technique to compute the Dolbeault cohomology. So the question is, what happens when J is non-integrable? Because we have the harmonic forms. This space is well defined once you fix the metric, but we do not have the right-hand side in this isomorphism. Okay, we do not have the Dolbeault homology. So this was the motivation for this question posed by Kodaira and Spencer at the beginning of the 50s. And then, well, they posed this question at a conference, and then Hirzebruch wrote this paper with listing all the open problems at this conference. So this was one of the open problems. So this is Hirzebruch's problem 20. So the question, well, this is not the whole question. The whole question is longer, but this is the part I'm interested in this talk. So the question is, are the Hodge numbers metric independent? Right? Because in the integrable case, they are. The Hodge numbers are the dimensions of the Dolbeault homology group. So of course, they are metric independent. But the question is, what happens if we take an almost complex structure? OK, so clearly, the answer is immediate if you consider special B degrees. If you take P0 forms, or by duality Pn forms, you have that HP0 del bar is an almost complex invariant doesn't depend on the metric, because the being harmonic, so let me write this down, so means that del bar of the form is 0, and del bar star of the form is 0. But if you have a P0 form, this condition is satisfied, and this is the only condition involving the metric. Okay, so P0 forms are holomorphic forms, essentially. Okay, so what happens for other B degrees? The answer to this question arrived around 70 years later by Holt and Zhang. So the answer is no, they are not metric independent. The Hodge numbers depend on the metric. And so Holt and Zhang showed an explicit example. They consider the Kodaira-Thurston manifold. So it's a 4-dimensional manifold. It's a nil manifold, if you want, admitting both complex and symplectic structures, but it's not Kähler. So they consider on the Kodaira-Thurston manifold, they construct an almost complex structure, non-integrable, of course. And then they show that if you pick they construct two different Hermitian metrics, and they show that H01 changes. And then in a second paper, actually, they showed that if you pick two different almost scalar metrics, again, H01 changes, okay?
The same symplectic form, the almost scalar case?
Sorry?
Almost scalar is compatible with symplectic form, so there's the same symplectic form or different symplectic form?
Two different symplectic forms compatible with the same almost complex structure, and they show that H01 is different for them, okay? And so how do they prove this? Well, the thing is they compute the harmonic forms. I mean, they solve the equation. They pick generic 0-1 form for that almost complex structure. They fix the metric, and they solve this equation. And they can do that because they are in dimension 4, and the Kodaira-Thurston manifold has a very particular structure. I mean, they use the torus bundle structure, essentially. OK, so just let me say in this slide a few words about the cohomological point of view. So in fact, we cannot define the standard Dolbeault homology, but Sirisi and Wilson gave a generalization of the Dolbeault homology in the almost complex setting. So let me go back a few slides just to tell you the definition. So if you notice, mu bar squares to 0. So they take the mu bar cohomology, and then using the fact that you have this relation and this other relation, you can show that the del bar operator is well defined on the mu bar cohomology, and it squares to 0 there. Okay, so using this, they define this cohomology. So they take the mu bar cohomology, and then they take the del bar cohomology of this cohomology. Okay. So clearly, if J is integrable, mu bar is 0, so this is the standard Dolbeault homology. So it's really a generalization of the Dolbeault homology. And yeah, so they studied this homology. But so let me just point out that since in this talk I'm considering only del bar harmonic forms, here in these classes, in the classes of this cohomology, you have mu bar closed form. So we have no relation in general if you take just the bar harmonic forms here. So you don't have an injection here. But if you take also mu bar harmonic forms, then yes. So in fact, a possibility in this setting is to consider another operators that gives the combination of both like del bar and mu bar and so on.
So in Sariski-Wilson, the key point in doing these computations is that since mu is a zeroth order operator, it's basically contracted with the Nienhaus tensor.
Yeah,
so in fact, the so-called cohomology, it's sections of some bundle.
Yeah, exactly.
It's an algebraic thing you get at every point.
Yes, exactly. But the point is that, so we have this nice cohomology, but Coelho-Placini-Stelzig proved that in general can be infinite dimensional. Okay, so you see, we cannot have an Hodge theoretical counterpart. I mean, because when I work with harmonic forms, these spaces are finite dimensional, but the Dolbeault cohomology here is infinite dimensional, so we have a gap between these two theories at this point. Yeah, it would be nice to understand how to bridge the gap in some sense. Okay, so however, if you spatialize to fourth dimension, Holt and Zhang proved the following fact. So if you assume that your metric is actually almost scalar, okay, so omega is a symplectic form compatible with J, then they proved that if you take, okay, so 0, 1 forms, the dimension changes. But if you take H1, 1, it's actually equal to B minus plus 1, okay? B minus usual notation, okay? It's the dimension of the space of anti-self-dual harmonic 2 forms. Okay, so if you have an almost scalar metric, H1, 1 is this one. I mean, it's fixed, depends on the topology, okay? So they posed, there is these questions. So take a compact four-dimensional almost complex manifold, which admit also almost scalar metrics, okay? So they question, there exists a non-almost scalar metric such that H11 is different to B minus, for B minus plus 1, okay? So, of course, answering to this question also means that H11 changes with the metric, okay? So I'm going to answer to this question in the following slides, okay? All right, so, and then this is the picture in dimension 4, okay? So in dimension 4, the Hodge diamond is this one, right? So you have these, Hodge numbers here. They are metric independent, as I said before, just for B degree reasons. Then you have H01, which is the one that changes with the metric, and it's actually essentially unknown, meaning that, for instance, I do not know if you fix the almost complex structure and you change the metric if you can make these numbers arbitrarily big. They can be arbitrarily big if you move both the almost complex structure and the metric. This was proved by Holt and Zhang. But if I fix J, I do not know how big can be H01. I do not know that. And then we are left with H11, which seems to be particularly interesting in almost scalar geometry, at least. Okay. So the first observation we did with Adriano Tomassini is the following. If we are in dimension 4, actually, H11 del bar is a conformal invariant. I mean, if you take two Hermitian metrics in the same conformal class, H11 doesn't change. I mean, Hodge star is not changing. Of course, you can do this in higher dimension. You pick PQ forms with P plus Q equal half the dimension of the manifold, and you have the same result, okay? But I'm interested in dimension 4. So what does it mean? It means that immediately, as a corollary of the result of Holt and Zhang, we have is that in your compact almost complex manifold of dimension 4, if you pick a globally conformally Kähler metric, so not an almost scalar metric, but another metric in the same conformal class, then H11 is again B minus plus 1 for the result I showed you before, okay? Okay, so this is the first observation. So now, in order to explain the following results, I have to do a little digression to talk about locally conformally Kähler metrics that were already mentioned by Andrei. So pick in any dimension a compact almost Hermitian manifold. So I will denote with L the usual Lefschetz operator, multiplication by omega, and lambda is the adjoint. So you can define the Lie form of the metric. So the Lie form of the metric, well, it can be defined in several ways. So just let me say that if you consider omega, okay, your metric, to the power n minus 1, I mean omega wedge omega n minus 1 times, and you apply the differential, in general, this will be equal to theta wedge omega n minus 1, where theta is a 1 form. Okay, so an Hermitian metric is called, let me say, strictly locally conformally Kähler if omega is not closed. Okay, so I'm taking the differential of omega, but it's equal to alpha wedge omega, where alpha is a declosed, non-de-exact 1 form. So in particular, if you want the relation with the Lie form defined before, you have this relation. So please, so in this talk, I will say strictly when I want to really point out that alpha is taken non-de-exact. And omega is called globally conformally Kähler if you have the same, but now alpha is exact. Okay, so it's the differential of a function, and the name globally conformally Kähler means it's exactly because if you take e to minus f omega, this is an almost scalar metric. Okay, and in this other case, in the local case, because alpha is just declosed, so it's not the exact, but it's locally the exact, so you can do the same locally. Okay, so if I have two metrics that are conformal, so let's say omega tilde is equal to phi omega with phi a smooth positive function, then the Lie forms of the two metrics are related by this formula. So you see here we have an exact part. So their differential is the same, and in particular, if one is exact, also the other one is exact. So I'm saying that these notions are conformal notions. I mean, all the Hermitian metrics conformal to a locally conformally Kähler metric are still locally conformally Kähler. And if they're global, same for global, okay? But of course, I mean, these metrics do not always exist on almost complex manifolds. But there is this other class of metrics already mentioned by Anna today that are Godeschon metrics, they always exist. So you can define them saying that DDC of omega n minus 1 is 0, or if you prefer, the Lie form is co-closed. And thanks to this famous result of Godeschon, we have that if you have a 2n-dimensional compact, almost complex manifold with n bigger than 1, then in every conformal class of an Hermitian metric, you can find a Godeschon metric. Okay, and well, this metric is also unique up to multiplication with positive constants. Okay, so Godeschon metrics always exist. And if you remember, in every conformal class, and I said before that in dimension 4, H11, that is the Hodge number I'm interested in, is a conformal invariant. So the idea would be, okay, let's compute this invariant using the Godeschon metric in the conformal class, okay? So let's go back to our setting. So we have a 4-dimensional, compact, almost complex manifold, and now fix a Godeschon metric omega. And so suppose that you have, so pick psi on a harmonic, Dobar harmonic 1-1 form, then psi can always be written as f times omega plus gamma. Okay, so you have the part, the part along omega and the traceless part. I mean, gamma is anti-subdual. So the point is that if psi is a harmonic, if psi is harmonic, then actually f turns out to be constant. Okay, it's not a function, but has to be a constant, a complex number, okay? So using this, we prove the following. So if you have a compact, almost complex manifold of dimension 4, and suppose that you have a strictly locally conformally Kähler metric, then H11 has to be equal to B minus. Okay, so what's the idea of the proof? Okay, you start with, let's say, omega tilde. Omega tilde is strictly locally conformally Kähler, but H11 is a conformal invariant. So in the same conformal class, now choose a Godeschon metric. So this metric will be both now Godeschon and locally conformally Kähler. So now we want to compute H11. So take a 1-1 form psi. You can write psi this way. and so psi is Dobar harmonic, so f is constant because the metric is go to Schön. But what we prove is that, we prove that actually f has to be 0. And why is that? Well, you just do some computation, and in the end, what you get is that the Lie form is this star exact. But the metric is strictly locally conformally Kähler, so it's also closed. So theta has to be 0, but it's not possible. Otherwise, the metric is almost scalar. Okay? So f is equal to 0. So it means that psi is actually just equal to gamma. And in fact, since psi is harmonic, you show that gamma is d-harmonic. Okay? So H11 is equal exactly to B minus. So essentially, what we have is the following. So we are in dimension 4, compact almost complex manifold. If you have a globally conformally Kähler metric, we said H11 is B minus plus 1. If omega is strictly locally conformally Kähler, H11 is B minus. But the point is, it seems that H11 depends on the metric, but this result has to be coherent with the integrable case, of course. I'm not saying that J cannot be integrable. It might be integrable. So this has to make sense on surfaces, compact complex surfaces, right? So what happens in the integrable case? Of course, H11 is an odd number, so it depends only on the complex structure. But if you have a compact complex surface, we know that the Kähler condition is a topological condition. This is a result of, I don't know, like Kodaira, Lamary, Buchdahl, Siu. So Kähler, the compact complex surface is Kähler if and only if B1 is even, and it's non-Kähler if and only if B1 is odd. But what you have is that if it is Kähler, if your compact complex surface admit a Kähler metric, H11 is equal to B minus plus 1. And in the non-Kähler case, H11 is B minus. Okay, this is for compact complex surfaces. But the point is that in the previous result, it seems that H11 can change with the metric in on your manifold. But the thing is that if J is integrable, you cannot have both globally conformally Kähler matrix and strictly locally conformally Kähler matrix. Okay, they cannot coexist on the same manifold. So this result is due to Weismann. So what I'm saying is that on compact Kähler surfaces, there exists no strictly locally conformally Kähler matrix. But in fact, it's more general than that. You can say this in any dimension. And actually, you can say it using just the Dobar lemma. You do not need the Kähler condition. So if you have a compact complex manifold, Weismann proved that if you have the Dobar lemma, then every locally conformally Kähler metric is globally conformally Kähler. Okay, you cannot have both metrics. But the point is, so what happens in the almost complex case, I want to show that I can have both metrics in order to say H11 varies with the metric. And in fact, we found an example in dimension 4. As far as I know, this is the only compact example of an almost complex manifold in dimension 4 that admit both an almost scalar metric and a strictly locally conformally Kähler metric. So in these two cases, we said before, thanks to our result, H11 is B minus plus 1 in the almost scalar case and B minus in the locally conformally Kähler case.
It seems to be just the conclusion that you can't have both a Kähler metric and a strictly conformal Kähler.
No,
on the same compact.
No, I can have both now. In the non-integrable case, I can have both. But in the integrable case, I cannot.
Oh, this does not depend on integrability.
No. I'm saying, so the point is here, I have an almost, I'm going to show you exactly the example, actually. But this is an almost complex manifold. And this manifold admit a compatible symplectic form, if you want, with H11 B minus plus 1, and a compatible different matrix, so let's say omega 2, that is strictly locally conformally Kähler. But this cannot happen when J is integrable, okay? This cannot happen. So in particular, as a corollary, H11 depends on the metric also, okay? So this answers also the question of Kodaira and Spencer, yes?
LCK is with respect to some other J, right? It's not with respect to the given complex, the almost complex structure. When you say strictly locally conformally
A different metric that is strictly locally conformally
But
Kähler.
So for omega 2, it's an integrable, almost complex structure for omega 2, but for omega 1, it must be non-integrable.
Why do, no,
Omega 2, you have another complex structure, right? Which
No.
is compatible.
no.
Same J.
Same J. So let me discuss. So the example is the Kodaira-Tarson manifold. Okay, so we have, so this is the standard definition, right, of the Kodaira-Tarson manifold. You have the three-dimensional Heisenberg group and quotient for this lattice, the standard lattice with integral entries, and times S1. So, here you can define this global frame of, let's say, of one form. So let me just put this here in evidence. So these are one forms, and we have the standard structure equations. So what we do, we define a family of almost complex structure, J, depending on a parameter that is not 0. And we define this coframe of 1-0 forms. Okay, fix A, any A, and you can define these 1-0 forms. And in particular, if you compute the differential of these forms, you see that J is non-integrable because you have an extra terms here, right? You have the del part, the del bar part, but then you have the extra term that says that J is non-integrable. So if you take this metric, this Hermitian metric, let me see, omega A, if you compute the differential, it's equal to theta wedge omega, where you show that this theta is closed, but it's not the exact. So it's strictly locally conformally Kähler. But in fact, you can change the metric. Okay, you have to put some condition on the parameter, but you can change the metric and show that JA admits a compatible almost scalar metric also. You show that this is closed, again, using the structure equation. So in fact, what you have is that on this family of almost complex manifold, you can find a compatible metric, say omega A, which is strictly locally conformally Kähler, so B minus, H11 is equal to B minus, which is 2, and matrix, say omega tilde, globally, almost scalar actually, with B minus, with H11 equal to B minus plus 1, which is 3. So this is the example. But in fact, these are the only two possibilities, B minus and B minus plus 1. You cannot have more. So in fact, you can show easily that B minus is a lower bound for H11 del bar in dimension 4, but in fact, the result can be improved because Holt proved that if you have a compact, almost Hermitian 4-dimensional manifold, then actually H11 is either B minus or B minus plus 1. You have no other options, okay? This was proved by Tom Holt. Okay, so this is the case for Dolbeault harmonic forms. Let me say a few things about Bott-Chern harmonic forms, because the Bott-Chern cohomology is very useful in non-Kähler geometry, so we also consider, okay, what can we say in this setting? You can define the Bott-Chern and Desprez Laplacian essentially in the usual way. And so again, with similar notation, the similar notation I used before, I will denote the space of harmonic forms with this H, calligraphic H, and the dimension with this small h. And here being harmonic, let's say for Bott-Chern, means that your form is closed. Okay, in the integrable case, it's closed. Here it's just del closed and del bar closed. It doesn't mean that the form is closed, and that del bar star closed. And clearly, if J is integrable, Schweizer's result proved that in every, let's say, Bott-Chern cohomology class, there exists a unique harmonic representative, okay? So in this case, Piovani and Tomassini, using, let's say, our technique, so the primitive decomposition of 1-1 forms, proved that H11 Bott-Chern is either B minus or B minus plus 1. essentially with in the same way we did for the Dolbeault case. But then Holt showed that actually B minus cannot occur. I mean, actually H11 Bott-Chern is always equal to B minus plus 1, okay? So only depends on the topology of your manifold. And again, so the idea for all these results is based essentially on the primitive decompositions of harmonic forms. So our question is, okay, so what about higher dimension? This is what we can say in dimension 4. So now let's move to higher dimension. As you will see later, actually, in order to say some things, at least right now, I need to assume the metric to be almost scalar. So, well, with the same notations I used before, so the Lefschetz operator is called L. So let me recall just this definition you all know. So P form with P less or equal than N is said to be primitive if lambda of the form is equal to 0, or if you prefer, you have this equation. So if you have a K form, you have this decomposition in primitive form. So every K form can be decomposed in this way, where here you have suitable powers of omega, and here these beta are primitive forms. And the point is that, so why I'm considering this primitive decomposition, because if I want to study harmonic forms, I need to consider the Hodge star operator, of course. But I do not know in general how the Hodge star operator acts on forms. But you have this formula whenever you have suitable power of omega wedge a primitive form, okay? And Series and Wilson proved that the primitive decomposition passes to the harmonic forms. If you take PQ forms that are harmonic for the exterior derivative, you have this decomposition, okay? So the question is, what about the other spaces of harmonic forms, okay? Well, yeah, of course, I mean, this is, well, actually, it's an observation. So in case of P0 forms, of course, they are primitive, so nothing to say, let's say. And also for the dual. So what about the other degrees, the other B degrees? So assume that you have a compact 2n-dimensional almost scalar manifold, then you can prove essentially this decomposition, let's say for H11 of Dobar. Essentially, what we prove is that here, instead of a function, you have a constant times omega, plus the primitive part that has to be Dobar harmonic. And dually for n-1, n-1. Yes, but we have to assume almost scalar. Actually, probably you can also take, they're called probably semi-Kähler, I think, when omega is not fully closed, but it's just Dobar closed. Probably it works also like that, but yeah. And similarly for the operator del, I mean the conjugate operator. But so let me just point out that you cannot expect the usual result you have in Kähler geometry here for harmonic forms. So what do I mean? Well, if you are in dimension 4, yeah, it's true that the Dobar Laplacian and del Laplacian coincide on 1-1 forms. So in particular, their kernel coincide. Okay? But in general, there exists almost scalar 6-dimensional manifold with H11 Dobar different from H11 of del. Okay, so, but recall that in the Kähler case, in the compact Kähler case, we have the Kähler identities, and so these spaces coincide. But as soon as you drop the integrability assumption, everything changes. I mean, you have the mu and mu bar operator. Actually, you can show that there is a relation between the Laplacian of Dobar, Laplacian of del, using also mu and mu bar. Okay. So how one can construct an example? So we consider the torus, 6-dimensional torus, and we considered an almost complex structure that is non-invariant. Actually, we were not able to find an example, I don't know, on a manifold, so manifold with an invariant almost complex structure we couldn't find one. The example we find is the following. So we have a function depending on x3, y3, and we define this j. So phi2, phi3 are the standard forms, right? But here phi1 is perturbed with the function. You can write down the structure equations. The only thing you have is that phi2, phi3 are closed, and here what you have the fact that G depends on x3, y3, okay? So you have this derivation. So if you define the standard matrix, so this omega, it turns out to be almost scalar. You compute the differential, it's closed using the structure equation. But you can show that, for instance, it's a computation. I'm not going to, do all the calculations, but phi1 to bar turns out to be not del bar closed, so it's not harmonic, of course, but it is del harmonic. Okay, so the two spaces are different. Okay. All right. So what about the Bott-Chern case? With Riccardo Piovani, who was a PhD student when we studied this. He was in Pisa. So we showed that. So we can say essentially the same for the Bott-Chern harmonic forms. He was mainly interested in Bott-Chern harmonic forms, actually. So I studied with him this case. For P0 forms, clearly they are primitive. So, this is an observation again. So essentially, with the same techniques I used in the Dolbeault case, we showed that if you have a compact 2n-dimensional, almost scalar metric, then you can find, again, this decomposition. So all the proof is, the main part is to show that you find a constant here, okay, complex numbers here. And dually for h n minus 1 and minus 1. And similarly, these decompositions hold for Epley harmonic forms. You can also, of course, consider this case. And again, as soon as you consider four-dimensional manifolds, let's say all the spaces of harmonic forms will coincide for 1-1 forms. Just B-degree reason, and you are in dimension 4, so there's not much space, but not much room. But more in general, even if you assume that you have a normal scalar metric, we can only find inclusions. So first of all, you can show that there are inclusions of Bott-Chern primitive forms into Epley primitive forms for P plus Q, of course, less or equal than n. And so in particular, using the decompositions we have an inclusions in any dimension of H11 Bott-Chern into H11 of Epley. But again, they do not coincide in general, okay? So as soon as you drop the integrability assumption, all the results you have for harmonic forms in Kähler geometry fall down, okay? So it's a very wild world in some sense, okay? So they do not coincide, not even in dimension 6 already, in dimension 6. Dimension 4, okay, but already in dimension 6, they do not coincide. Yes, but for Kähler manifolds, of course, they coincide thanks to the Kähler identities. So in dimension 6, this is if you want the Hodge diamond or the Bott-Chern diamond, we only have these numbers. So for blue numbers, we have the decompositions. So these numbers here, here, and here. So for H11, H22, we have primitive decompositions. Okay, so we are left with H21, H12, where we didn't know what happened. And so in fact, so let me show these two results. What we have is that already in dimension 6, again, we don't have the composition for H12 and, H21, both for Dolbeault and Bott-Chern. So the thing is that really you do not know what to expect. As soon as you drop the integrability assumption on J, you do not know what to expect on this Hodge number, on the spaces of harmonic forms, because the behavior can be very different from the Kähler case. Yeah, and I think, yeah, I can stop here, so I'm very on time.